సరే ఉన్నారు. Dear students, good evening. The faculty has got the power failure. Class will start by 5:15. Please wait until the class start. Class will start by 5:15. 5:15.
Right. శేషు స్టార్ట్ అయింది. ఆగు, నేను కాల్ చేస్తా. Right. So I'm back. So please try to excuse me because of this power issue. I could not start the class by time because of these heavy rains. So here this power issue. So that is the reason. Anyhow, I did some alternative. Why? Because I don't want to cancel or miss the class. So that is the main intention. Anyhow, we'll start. Is it clear from my side? All of you, raise the hands. All right. So we'll start today class. So right. Today it's day 9, 14/07/2021. Right. So I'll start. Now before I start, please confirm me once. So this videos streaming, audio and other things are clear from my side. Please confirm me, all of you. Right. So I'll start. Right. So yesterday we are able to derive an important relationship between the rotor input, rotor losses, the rotor output. Right. So what is that very important relation we had yesterday, if you recall? So rotor input. So we have used P suffix Ri for the rotor input or rotor losses, rotor output is equal to 1 is to S is to 1 minus S, right? So basing on that, already we had one observation. What is that? Rotor efficiency is equal to NR by NS, that is equal to 1 minus S. This is what we have seen yesterday, right? Basing on that, we have seen one numerical also, right? If I am correct, please confirm me, all of you raise the hands. Right, done. Yesterday, one of the students during this question and answer, sir, you told that the rotor speed has to be always closer to synchronous speed. Yes. So who decides or who designs? The manufacturer will decide. How will decide? Means basing on the torque slip characteristics. So these torque slip characteristics will be basing on the resistance, reactance, and other things. So I'll be just postponing this issue. On what basis we are going to decide that the rotor speed has to be very closer to synchronous. So which parameter decides that? We'll see that in the coming sessions, right? Don't worry. The second thing is the approximate equation for the motor efficiency. Approximate equation for motor efficiency. It is 1 minus S by 1 plus S, right? So there is no formula for this. So basing on a thumb rule, just it is given like 1 minus S by 1 plus S. On what basis? See, I'll give an example. I'm having a small kid. See, I'm just asking him to just go and come a little distance. At every time he's going like 4 meters, 4.1 meters, 3.9 meters, 3.8 meters, like 3.9 meters, like he's going. Then basing on this analysis or basing on this report, I can analyze that this kit can travel a maximum distance of 4 meters. It is something like basing on the conditions, basing on the experiments, basing on the values, we can decide the kid in that instant can have a distance of maximum up to 4 meters. Why? Because we have seen that out of his previous experience. So what is the distance he is able to travel is 4 meters. Then I can say maximum that kid can travel for that time up to a 4 meters distance. Is it clear? Is it clear? Why? Because when I have tested for 5-6 times, what is the distance he's traveling is something 4 meters he's traveling. So basing on that, I can decide. So that kid can have a maximum distance he can travel is 4 meters. So here also, basing on the numericals. So if anyone just want to approximate the efficiency of the motor, it is 1 minus S by 1 plus S. It is only a thumb rule. It is only an approximate formula. So there is no like particular derivation for this, right? But one thing to be noted here is you are not supposed to use this formula for calculating the motor efficiency when the powers are given. What do you mean by that? See, a three-phase induction motor draws 40 kilowatts of power when it is operating at a slip of 4%. The stator losses are something, the rotor losses are something, the mechanical losses are something given. Calculate the efficiency of the motor means in that case you cannot use this formula. So when you can use this formula means only when that slip information is given. What is that slip information? Yes, information is given. So whatever the example I took, in that case you have to follow the procedure. What is that? Stator output is equal to input minus losses. Rotor output is equal to rotor input minus losses. Like that, gross power is equal to, or net power is equal to gross power minus mechanical losses. Like that, you have to follow the procedure to calculate the efficiency. When you can use this formula means only when the slip information is given, not in all the cases. So can I say only when, only when, only when slip information is given, only when slip information is given. Slip information is given. Only when slip information is given. Is this point clear? Confirm me all of you. Is this point clear? Confirm me all of you. Right. Next, the third point is, so what is that we have seen? NR by NS is equal to, NR by NS is equal to 1 minus S. Correct? So from this, NR is equal to NS into 1 minus S. This I call it as a basic speed equation. Basic speed equation. Basic speed equation. Basic speed equation. So tomorrow if anyone questions you, Are Baba, can you please tell me what is the equation we are having to find out the speed of an induction motor? So NR is equal to NS into 1 minus S. So now we are able to find out one, or we are, now we can say we are having an equation for finding out the speed of an induction motor. It is NR is equal to NS into 1 minus S. Is this point clear? Is this point clear? Right. Now, basing on this, I'm trying to decide few things. What is that? What is the operating range of a slip? Operating range of a slip. A range of a slip. Of a slip. So it is 2 to 8%. 2 to 8%, right? We already told you the speed should be closer to that. So this is the no load speed, slip. This is the full load slip. So if I consider the no load slip as something like 2%, what is the meaning of no load slip? When the load on the motor is almost zero. So it is the no load slip. It is 2%. It is 0.02. Then what is the equation for the rotor speed at no load? That is equal to ns into 1 minus SN. So how many pole machine already I had taken yesterday? It is a 6 pole. So it is 1000 into 1 minus 0.02. So it is equal to how much? 980 RPM. So what is the rotor speed at no load? It is 980 RPM. Then full load. What is the meaning of full load? Means when the motor windings are carrying the rated current. I'll tell all these things, don't worry. Full load slip is say 8%. So it is 0.08. Then what is the rotor speed at full load? Rotor speed at full load is equal to 1000 into 1 minus 0.08. Then what is the speed here? It is 920 RPM. Then I want to find out the percentage speed regulation. Percentage speed regulation. That is equal to the rotor speed at no load minus the rotor speed at full load by the rotor speed at full load into 100. See, it is just something like in case of your transformers, when you are calculating the voltage regulation, it is the no load, the secondary no load voltage minus full load voltage by no load voltage. Because whatever the nameplate details we have in case of transformer, they are the no load voltages. So that is the reason we divide with the no load voltages. But when I'm talking about the generators or these motors, so whatever the speed or whatever the voltage that is given the full load voltage, so that is the reason you have to go for full load. So in case of motors, it is a full load. Why? Because if you look into the nameplate details, so whatever the speed that is given is a full load speed. So here what will be the case here? So it is 980 minus 920 by 980, so 920 into 100. So can you please tell me what is the answer for this? Can you please text me the answer for this? 6.52, correct? 6.2%. What speed regulation is? It is 6.52 or 6.5. So 6.5, very good. So what is that observation? Yeah, 6.5 to 6.12. So it cannot be 1 to 6.52, I think. Okay, 6.52. Even I can check here also. Calculator. Okay, no need. 6.52 enough. It is enough. So what is that observation? You can see here the change in speed from no load to full load is almost neglected. You can see this change is almost neglected. Why? Because there is no much change in the rotor speed from no load to full load. Why? Because if anyone say I have invested 100 rupees, but I got only 94 rupees. So 6 rupees you have lost. Then in that case, I can say that loss can be neglected. That loss can be neglected. It is not 65.2, Baba. It is 6.52. 65.2 is a too large value. It is 6.52. Once you check Vikram Pujar, please. Right? So you can see there is no much change in the rotor speed from no load to full load, as there is no much change in the rotor speed from no load to full load. So these motors can be treated as a constant speed motors. What is the meaning of a constant speed motors? Means there is no much change in the rotor speed from no load to full load. The speed will be almost constant. But it doesn't mean that unlike your synchronous motor, the speed will always remain ns. No, there is a slight change in the speed, but that change can be neglected. There is no much change in the rotor speed. Why? Because when compared to the full load speed, that change is very less, so I can ignore that change. So for that reason, we can treat the induction motors are also as a constant speed motors. So this is also one of the interview questions. Can you please justify why the induction motor called as a constant speed motors? Yes, the reason is, yes. So what happened? From my side, I'm clear. So all of you raise the hands if you're clear with my audio, video, and other things. All of you raise the hands. No, just 1 second. Let me check the network. Now it is clear. Raise the hands. If it is clear, all of you raise the hands. Right, done. So can I say there is no much change in the rotor speed from no load to full load? So this change is very less. That means when compared to your 920 RPM, the change is only 60 RPM, right? So when compared to 920 RPM full load speed, the change is very less. So hence we can treat these motors are also as a constant speed motors. But unlike your synchronous motor, the rotor speed will not be always synchronous speed. So here there is some slight change in the rotor speed from no load to full load. So what is that no load? What is that full load? I'll explain in detail. Don't worry. So as there is a slight change, so this change can be neglected and these motors can be treated as a constant speed motors. These motors can be treated as a constant speed motors. Is it clear? Confirm me all of you. Confirm me all of you. Right. So can I write? Can I write like this? As there is no much change in the rotor speed or in the motor speed from no load to full load, no load to full load, the induction motors can be treated as constant speed motors. Constant speed motors. I hope this point is clear. All of you confirm with me. Is this point clear, all of you? Right, done. So this is the third point, right? Done. The fourth point is what is the equation for the rotor current? So rotor current I2 is equal to, if you remember, it is E2 naught by square root of R2 by S whole square plus X2 naught square. This is the equation for the rotor current, right? Done. But you know that the machine is always operated with low slips. So for low slips, what is the operating range for the induction motor? 2 to 8%. For low slips, NR will be closer to NS and slip will be approximately equal to 0. In that case, R2 by S whole square will be much greater than X2 naught square. So here you can see in the denominator, I can ignore X2 naught whole square. Why? Because when compared to R2 by S whole square, for low slips, that X2 naught whole square will be much lesser. Then in that case, I2 is equal to E2 naught by R2 by S. Then if I take this, I2 is equal to S E2 naught by R2, R2, right? So this is only for which slips? It is for low slip operations, for low slip operations, low slip operations, low slip operations. So here you can make one point. What is that? For low slip operations, I2 is directly proportional to S. Why? Because E2 naught is a fixed value. Why? Because it is a EMF induced in the rotor winding at standstill. So it is a fixed value. And R2 is the design parameter, the rotor winding resistance. It is also fixed. So for low slip operation, what is the relation we are having between current and slip means directly proportional. So basing on that, they may frame a question. What is that? When the operating slip of an induction motor is 2%, the rotor current is 4 amperes. When the slip is doubled, what will be the value of the rotor current? It is a doubled. Why? Because the relation is directly proportional. Is this point clear? Confirm all of you. Confirm all of you. So can I write note here for low slip operations? For low slip operations, low slip operations, rotor current is directly proportional to slip. Slip. I hope this point is clear, right? So before I proceed, so there is a small announcement. See, actually, tomorrow you are having holiday on Saturday, right? If I'm correct, confirm me. Generally, yes. But that holiday is preponed to tomorrow, Thursday. That means the coming Thursday means tomorrow there is a holiday for you. On Saturday there will be a class. There is no holiday. And I mean all batches, so that it is not like holiday for tomorrow. So for only induction motor there is a holiday tomorrow. On Saturday we'll be having the class. But tomorrow, for the other batches, other than the new batch, the previous power system batches, for them, there will be a faults and stability class. Once again, I repeat. So for the new batch, tomorrow is a holiday, Saturday is a class. So we have class on Saturday. It is not a holiday. But for other old batches, so the leftover topics in faults and stability power system will be continued, right? Tomorrow you don't have holiday for the old batches, only the new batch, only for induction motor there is a holiday. But other people, those who are taking the previous batches, so they will be having faults and stability. Is it clear? Confirm me. Confirm me. Raise the hands. Right. Right. So tomorrow I'm not going to come. Again, I'm going to come on Friday and Saturday we'll have the class. Right. Done. So please get ready with the calculators and try to give the answer for this. Please try to give the answer for this. See all of you. I'll try to give one numerical, please. Right. So problem. A three-phase 400 volts, 50 hertz, 6-pole slip ring induction motor, SRM slip ring induction motor has a star connected rotor windings. The star connected rotor windings with rotor winding resistance per phase as zero point 0.1 ohms, right? 0.1 ohms. If the voltage across any two slip rings at standstill is 100 volts, what is the value of rotor current rotor current when the motor operates at a slip of 4%. Option A 10 amperes, option B 5 amperes, option C 5.77 amperes, option D 4 amperes. Please answer this. I'll give 2 minutes time. 2 minutes time. Please do this. Get ready with the answers, all of you. Slip range in per unit is 0.02 to 0.08, right? Please. Anonymous attendee, sir, why you are calling it as a holiday? See, a holiday I'm with respect to my induction motor I'm talking. But for the previous batches, you are having power system. Induction machine is holiday. Please remember. Right? Okay, answer is D. D. What is the D? 4 amperes. So D. So some are giving 5.77, 4 amperes. Option C, 5. C. Option D, option 4 amperes. D, 5.77. Anyhow, please stop. I'll do it. I'll do it. See, you know that the rotor windings are always connected in star. The reason already you have learned. So these are the rotor windings which are connected in star. Star. And you know that the rotor windings are brought out with the help of the slip rings and pressure. And what is that given? If the voltage across any two slip rings at standstill is 100 volts. So please remember that. So he has given the voltage across any two slip rings at standstill is 100 volts. So standstill means when the rotor is stationary. But whatever the voltage that we have between the two slip rings is a line voltage. But in all our calculations, we need the phase voltage. So E2 naught per phase is equal to 100 by root 3. Why? Because the windings are connected in star. So 5.77, 57.7 volts. Then what is the slip given? 4%. So what is the per unit? 0.04. What is the value of R2 given? 0.1. As it is low slip, generally less than 10%, we treat it as a low slips. So I2 is equal to S E2 naught by R2. So that is equal to 0.04 into 57.7 by 0.1. So what is the answer? Can you please tell? So a small rectification correction. So it is resistance is take 0.4, not 0.1. So 0.4. Let me take 0.4. Correction. 0.1 means you will not get correct answer. So what is the answer I'm getting here? 5.77 amperes. Right? But unfortunately, if you take E2 is equal to 100 volts, 100 volts, then answer would have been something like 10 amperes. Correction, Baba. Correction. Here R2 is not 0.1. R2 is 0.4. Please try to correct. Right? Printing mistake. 0.4. So in that case, it is 5.77. But if you take that E2 naught as 100 volts, then in that case, the answer could be 10 amperes. So here, the answer could be 10 amperes and the answer can be 5.77 RPM, sorry, amperes. So which one is a correct one means that 5.77 is a correct one. Why? Because in all the equation, what are those values we need to take means we have to take as phase values. Why we need to take a phase value? The question comes. Can anyone give the answer? Why we need to take phase values? See, Y connection is always star. Vikram, you please refer to my notes. I have spent some time why the rotor windings are connected in star, right? Please, you just refer to my notes. Yeah, please. Right? So can you give the answer? Windings are designed based on phase currents. Line current is maximum. Resistance is per phase. Pharma is divided per phase. Equivalent circuit is per phase. Resistance is per phase. Resistance is always per phase. We want to calculate only phase. Winding impedance per phase. The system is balanced. Everything taken per phase. Equivalent circuit is per phase. We represent circuits per phase. Yes, enough. 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 See, one thing, I think you know the basics of a circuits. Every time I cannot explain. In circuits, your teacher might have defined the definition for impedance. What is the definition for impedance? It is the ratio of voltage phasor to current phasor. So what is the definition for impedance? Means it is defined as the ratio of voltage phasor to current phasor. So that is the reason while you are calculating the impedance of a unknown resistor, it is R. How? If you just recall, just I'm trying to explain in brief. So if I'm applying a voltage of say V of t is equal to Vm sin omega t, this is the sinusoidal representation or the instantaneous, the sinusoidal or instantaneous representation. I can represent this phasor as the RMS value at an angle 0. Then what is the equation for the current? Current is equal to this V bar by R, voltage by resistance. If that is the case, I'll get Vm by R root 2 at an angle 0. So this is that I bar. Then if I want to calculate the unknown impedance of that resistor, so what is the definition for impedance? Impedance is defined as the ratio of voltage phasor to current phasor. What is that voltage phasor? Vm by root 2 at an angle 0. Vm by R root 2 at an angle 0. This cancel, this cancel. So it is R. So what is the basic definition for impedance? Means the basic definition for impedance is the ratio of voltage phasor to current phasor. So whenever you are using impedances to calculate current, that voltage should be a phase voltage, then the obtained current will be the phase current. So that is the reason always in all our calculations, whenever you are using impedances, the voltages has to be phase and those currents, whatever you get will be the phase. Why? Because by definition, impedance is the ratio of phase voltage to phase current. So whenever you are calculating the current using impedance of that branch, then you need a phase voltage. So you need a phase voltage. I hope this point is clear. Confirm me, all of you. Confirm me. Right. So here what I want to do means I want to calculate the phase currents. I want to calculate the phase current. So if I want to calculate the phase current, I need the phase voltage. That means the voltage across this phase I need. So, but what is that given? The voltage between the two slip rings. So the voltage between the two slip rings is a line voltage in this case, but I need a phase voltage. You know that in case of a star connection, the phase voltage is 1 by root 3 times of the line voltage. So that's the reason I got this. So as the slip is this, as the resistance is 0.4, then this current is 5.77 amperes. But if you take that 100 directly, then what is the answer? You'll get 10. So if the same question is asked tomorrow, so you'll be having two answers in your hand, 10 amperes and 5.77. Unfortunately, if you put 10 amperes and if you feel that your answer is correct, so no, it is wrong. Why? Because you have taken a line voltage, but in that calculations, you have to take it as a phase voltage. Is it clear? Confirm me. Confirm me, all of you. Right, done. So this is one analysis. So please remember in all our calculations, tomorrow when we are doing any calculation, so whenever the terminology three phase is given, so the given voltage will be a line voltage, but line voltage is a joker. In all our numericals, we need a phase voltage. So that is the reason whenever a three-phase circuit is given, then you have to see whether the given windings are star connected or delta connected. Like that you have to check. I hope this is clear. Confirm me all of you. Right. Then I'll take one more problem. Get ready. One more problem. Get ready. So this question was asked in the previous competitive exam. Get ready. The input to a three-phase 400 volts 50 hertz 6-pole induction motor while it is operating at a speed of 960 rpm is 40 kilowatts. 40 kilowatts. The stator losses total 2 kilowatts and the mechanical losses are 1 kilowatt. 1 kilowatt. Then the motor efficiency is dash. Do it. I'll give some time. Motor efficiency is dash. See why inductance is neglected. And Baba, consider a pure resistor. Please remember that. Sir, R2 is 0.1 now. No, we have to take it as 0.4. That's the reason I told. So 90, anonymous attendee 90%. Still 48.9, 88.7. Screen is not visible. It may be from your side, Monica, but I can see the screen. 88.7. 92.5. See, don't use 1 minus s by 1 plus s. That is wrong. I told you that. So whenever that powers are given, you are not supposed to use that formula, Yogesh. You cannot use that. 92 Sai Charan Reddy, you cannot use that formula. 1 minus s by 1 plus s. Please remember that. 90%. 88.7, 92.5. One show full question. Yeah, I can show full question. Yeah, you can see full question. Meghana. 92.5. So the major answers are 92.5 and 88.7 something. Thank you, ma. So here the stator input is given as how much? The stator input is given as how much? 40 kilowatts. And the stator losses are given as 2 kilowatts. 2 kilowatts. Then what is that stator output means? It is the stator input minus stator losses. And this is nothing but the rotor input. So it is equal to 40 minus 2 is equal to 38 kilowatts. Right? Done. Then here I need to calculate the rotor output. But there is no information given about the rotor losses. But when there is no information given, it doesn't mean that the rotor losses are neglected, right? You have to use some formula. What is that? Rotor input, rotor losses, rotor output is equal to 1 is to S is to 1 minus S. So you can calculate rotor losses, or without rotor losses, you can calculate rotor output directly. So rotor output is equal to, a rotor output by rotor input is equal to 1 minus S. So from this, the rotor output is equal to rotor input into 1 minus S. So that is equal to, what is the rotor input? We have 38 into 1 minus 0.04. How to calculate slip? So how many pole machine it is? P is equal to 6, F is equal to 50, and what is the value of Ns? Ns is equal to 1000 RPM. What is the speed at which the motor is operating? It is 960 RPM. Then what is the slip? Slip is equal to 1000 minus 960 by 1000. So it is 0.04. Then what is the value of this rotor output? Can you please tell me now? What is the value of rotor output? 38 into 0.96. What is the answer? 36, 38, 36.48 kilowatts. So this is nothing but your internal mechanical power developed. Then I need to calculate P net. So what is the formula for P net? P net is equal to internal mechanical power minus mechanical losses. So 36.48 minus 1. So it is 35.48 kilowatts, correct? Then efficiency of the motor is equal to P net by PSI into 100. So that is 35.48, right, by 40 into 100. How much it is? Tell me how much it is. So 88.7. So 88.7%. So I think it is clear. 88.7%. Those who are given 88.7 is correct, right? Other people, please try to rectify that. So this is the question. All right. So I'll ask next question. For the above problem, for the above problem, for the above problem, calculate the rotor winding resistance per phase if the current is, if the rotor current is 40 amperes. Do it. I'll come in a while. Just do it. Just do this. the answer? Point 0.31667. 0.31667. Okay, correct. We'll see. We'll see. Don't worry. So here, as for the above problem, so right, I'm just trying to work out this. Help me out. So here, the rotor input is given as, we got it as 38 kilowatts. Already have seen this. What is the relation we are having between rotor input, rotor losses, rotor output? Means 1 is to S is to 1 minus S. So if I relate these two, rotor input by rotor losses is equal to 1 by S. So from this, rotor losses is equal to slip times the rotor input. That is equal to 0.04 into 38 into 10 power 3. So if I'm correct, 1520 watts. Correct? Is this clear? Confirm me once. Is this clear? 1520 watts. Right, done. And you know that this is equal to 3 I2 square into R2. So from that, R2 is equal to 1520 by 3 into 40 square. Then if I solve this, 0.316 ohms. This is the answer. Please confirm if it is clear, all of you. Raise the hands. Right, done. So this is the second problem, right? The next problem is, see one thing. So you are having ebooks, right? So if you search your Google or internet, you are having ebooks of Nagaratan Kotari, electrical machines. Like many ebooks are available. So as soon as these concepts are over, so it is your fundamental responsibility to sit and to work out all the examples. So morning, one of the student was asking a doubt on these power stages. See, don't follow the procedures given in that book or in that textbook. Follow the explanation what I had in the class and check with the answers. The answers will be same. So please, when you are looking into the problem, you have to see only the problem, but not the answer. You have to do the answer by your own. Then finally you have to cross check the answer. It doesn't mean that that answer and this answer should be different. No, if your procedure is correct, then your answer and that answer should be same. Please do that. But very unfortunately, if you're getting different answers, even after following the same procedures which I explained, then WhatsApp on me, WhatsApp to my number, I'll check and I'll confirm whether your answer is correct, that answer is correct. But 98%, the textbook answers will be correct, right? So they will not be wrong. 1 or 2 will be wrong, but 98% they will be correct. So please try to do that. Is it clear? Confirm me, all of you. Right. So tomorrow I list out the books which are available on internet, on net. So you can download those books and please try to collect as many numericals as you can. Right. So if you want me to give the questions with only questions and you can do it, the answers means I can share the questions. Right. So I'll provide a soft copy of questions. Right. Say power stages we have done today. So I collect all the questions on these power stages and I'll just give one copy to you. Copy means I'll ask that manager to keep that copy and you can work out the numericals on that. Is it okay if it is correct? Is it okay? Right. So like that on every topic, I'll give some questions so you can work out the questions from that along with the answers. So on last day, if you're not getting the answers, we'll try to solve those answers, right? So that will make. Is it okay? Confirm me, all of you. Right. So remember one thing, practical, it is not possible to solve 100 numericals, right? But I'm sure that I'm confident that I know that whatever the concepts I'm giving to you, using these concepts, you can solve all the numericals from all the textbooks. I know that. Please remember that, right? Please. Anyhow, we'll proceed, right? Next question. Yeah, basics to advanced. I'll give all, don't worry. Right, don't worry. Sir, don't we use current equation for low slip? Yes, we can use. Yeah, so one of the question anonymous attend is, sir, don't we use current equation for low slip operation? Yes, you can use. But remember, in this question, E2 naught is not given, right? The first question is different, this question is different. So one of the student told that can't we use this current equation? Yes, you can use. So he mean to say that he want to use this I2 is equal to S E2 naught by R2. So from that he want to calculate R2, but you cannot take E2 is equal to 57.7. So this is for this question and this question is different. So in this question there is no E2 not given. Then you have to follow this procedure. If E2 not is given, you can use that procedure. Anonymous attendee. Is it clear? Right. Done. Fine. So please, one of the student has shared that book. So please do that. Right. Done. Next question. Next question on this power flow. Please see. Next question. Please see. A three-phase 15 kilowatts, 400 volts, 50 hertz, 4-pole induction motor has a full load speed of 1440 rpm. What is the full load shaft torque? Shaft torque dash, right? Now how to find out this answer, right? Fine. PRI formula. So there is PRI formula is 3I2 square into R2 by S. Sai Charan Reddy, right? Please. Then how to calculate the shaft torque? Now the question comes. If I want to calculate the shaft torque is equal to P net by omega R. As you are calculating the shaft torque at full load, then it should be P net at full load by omega R at full load. So that is P net at full load by omega R is 2 pi rotor speed at full load by 60. Now what is the value of this net full load net power? So remember, the only twist, this question was asked in GATE for 2 marks. Unless and until specified, this given power is always a full load output net mechanical power. Full load output net mechanical power. Why? Because say if I'm an examiner, I want to frame a question on a particular induction motor. If that is the case, what I'll try to do means I'll go to that induction motor and I look into the nameplate details and I collect the information from the nameplate details. Basing on that nameplate details, basing on that motor data, I'll ask a question about that motor. So here, whatever the data that is given here is collected from the nameplate details. That means a three-phase, the stator is having 3 phases, 400 volts, the voltage what we need to apply between the voltage should be 400. The supply current should have a frequency of 50 hertz. It is a 4-pole and 15 kilowatts. So it will produces a output mechanical power at shaft, which is equivalent to 15 kilowatts of electrical power. So 15 kilowatts. So unless and until specified, the given power in the numerical is always the full load output mechanical power. The full load output mechanical power. Sir, in the previous case, you have taken it as input na, but you can see here, it is mentioned clearly. It is mentioned clearly. So the input as 40 kilowatts. So it is given clearly that the input has 40 kilowatts, but here he has not mentioned whether it is an input or output. So in that case, you have to take the given output as a full load output mechanical power. Why? Because whatever the data that is collected will be collected from a nameplate details, and that nameplate details will always give a output parameters, a full load output parameter. So what is the full load output power? It is 15 kilowatts. If that is the case, so it is 15 into 10 power 3 by 2 pi into 1440 by 60. So what is the answer? Can you please tell? 9.947 Newton meter. 9.947 Newton meter. I hope this is clear, all of you. Right? Right? So can I say like this? So unless and until specified, unless until specified, until specified, the given power in any numerical is the full load output, full load output mechanical power. Mechanical power. Mechanical. I hope point is clear. All of you raise the hands if it is clear. Right. So this is something about your power stages and power flow. I repeat, I'll revise once again. Or as of now, what is that you have discussed or what is that you have completed means. So after that working principle is over. So our journey is to find out the performance of an induction motor using its equivalent circuit. So if I want to find out the performance of an induction motor using the equivalent circuit, first of all, I should know the equivalent circuit of an induction motor first. By the way, what is an equivalent circuit means? So it is not 9 point, so 99 point. So correction, 47 Newton meter. Please check this, right? Not 9.9, right? So if I want to find out the performance parameters, then I should represent the machine electrically. Why we need to represent the machine electrically means among all the calculations, which calculations are simpler means the electrical calculation. So that is the reason we need to represent the machine electrically. So as of now, which side we have represented means the rotor side. We have represented the induction machine. And with respect to that rotor side, if you want to calculate anything, so we have some formulas. What is that? If the rotor resistance and the rotor voltage and currents are given, and if you are asked to calculate what may be the rotor input power means 3I2 square into R2 by S. Like that, what may be the rotor losses means 3I2 square into R2, like we have seen with respect to the rotor circuit. And after that, we have solved some relation, we brought some relation between the rotor input, rotor losses, and rotor output. And after that, we have solved some numericals. Please remember, in most of the numericals, the rotor copper losses will not be given. But it doesn't mean that we have to neglect the rotor copper losses. When the rotor copper losses are not given, in that case, you have to use that relation. Rotor input, rotor losses, rotor output is equal to 1 is to S is to 1 minus S. Using that relation, you have to calculate the output. Unless and until specified, you cannot neglect the rotor losses. At least you have to consider the rotor copper losses. Why? Because you are neglecting the core losses. So minimum you have to consider the rotor copper losses. If you are neglecting, then your answer would have been 92.5 something else. So you cannot neglect the rotor copper losses unless and until it is given as neglected. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So we have calculated the rotor input, rotor losses, the rotor output. The next one is, what is that equation to calculate the electromagnetic torque? The next and very, very important thing is basic torque equation. Torque equation, right? And we call this basic torque equation as electromagnetic torque. Already I told you. So your DC motor, induction motor, synchronous motor works on electromagnetic torque. What is that electromagnetic torque? If a current carrying conductor is placed under a magnetic field, current carrying conductor. So current is electric field under magnetic field. If a current carrying conductor is placed under a magnetic field, So that conductor will experience as a force. So your DC motor works on that principle, induction motor works on that principle, even your synchronous motor works on that principle. Now I need to find out the magnitude of the electromagnetic torque of a particular induction motor when it is operating at some slip, when the rotor circuit parameters are given. So we are trying to build up, we are trying to derive some equation to calculate the values numerically using that equivalent circuit parameters, right? So it is a basic torque equation. So otherwise it is also called as electromagnetic torque. Magnetic torque. It is also called as internal torque. These are all the names given to this motor. Internal torque. Internal torque. So that torque which is responsible to twist the rotor, twist the rotor. The external torque is the torque which is available for twisting the load, right? So these two torques cannot be same. Why? Because in between you are having frictional torques. So the losses will be there. So the torque which is responsible for twisting the load is not responsible. I mean, this is not equal to this internal torque. Both the torques will be different, right? I hope this is clear. Confirm me. Now we are talking about which torque? The gross torque, the true torque, the internal torque, the electromagnetic torque. We are trying to derive that formula, right? See. So if you just recall this power flow, if you recall this power flow, we are giving a three-phase supply or electrical power to a induction motor. So what is the nature of that power? Electrical power. And this power, after some losses in the stator circuit, will travel the air gap and goes to rotor. So what is the nature of that power that is going to the rotor? Means again, still it is electrical. Still it is electrical. After some losses in the rotor circuit, that electrical power is converted into mechanical power. So the input to the rotor is electrical, but whereas the output of the rotor is the mechanical. So who is converting that input electrical power of the rotor to mechanical means the electromagnetic torque. So with the help of that electromagnetic torque, we are turning the rotor with a speed of nr, right? So that the output power is the mechanical power. So input is electrical, whereas the output of the rotor is mechanical. So who is responsible for producing that mechanical means electromagnetic torque. So with what speed it is rotating the rotor means nr. Is it clear? Is it clear? Is it clear? So here the rotor output is mechanical form. Mechanical form, it is due to that electromagnetic torque which is rotating the rotor with a speed of nr. Nr is here omega 2 pi nr by 60, right? So I'll try to modify something. So here it is the rotor output power, and this is the electromagnetic torque. Electromagnetic torque. I need to find out the magnitude. Torque. Right? Done. Fine. So you know one relation. What is that relation? Rotor input, rotor losses, rotor output is equal to 1 is to S is to 1 minus S. So from this, can I write rotor output by rotor input is equal to 1 minus S. So from this, the rotor output is equal to or rotor input into 1 minus S. I can write. I think this is clear. Confirm me all of you. Similarly, you know that NR is equal to NS into 1 minus S. So what I will do means I'll divide on either side with a 2 pi by 60. If I do that, so omega R is equal to omega S into 1 minus S. So I'll substitute this and I'll substitute this in this equation. In this equation. So in place of rotor output, I'll write this. In place of omega R, I'll write like this. So can I, if I write like this, so what is that? In place of rotor output, I can write rotor input into 1 minus S is equal to electromagnetic torque into, in place of omega R, I can write omega S into 1 minus S. Then you can see here 1 minus S, 1 minus S will get cancelled. Then from this, electromagnetic torque is equal to 1 by omega S into the rotor input. Rotor input. So if you want to calculate the electromagnetic torque, it is the rotor input by omega S. Till now, I was trying to tell one thing. If the rotor circuit is highly inductive, the active power drawn will be less. The torque which depends on that will be less. So that is the reason yesterday I have taken some time to explain why the starting torque is less. So at starting, the rotor frequency is equal to the supply frequency. So the inductive nature of the rotor circuit will be more compared to the resistive part. Because of high inductive nature, the rotor power factor will be less. Then the active power drawn by the rotor will be less. The torque, the starting torque, which depends on that power, will be less. But once the motor starts rotating, as the frequency of the rotor circuit start decreasing, the inductive nature starts decreasing, the resistance start dominating, then the power factor will increase, the active power drawn will increase, the torque which depends on that will increase. So that's the reason the running torque is more, right? Is it clear? Confirm me, all of you. Right. But in case of slip ring induction motor, what is it you're doing? As inductive nature is strong, as inductive nature is more at starting, we are adding some high resistance in the rotor circuit at starting. So when you're adding some high resistance in the rotor circuit at starting, you're making the rotor circuit highly resistive by adding some resistance. When you are making the rotor circuit highly resistive, then you can see the active power drawn by the rotor at starting will be very high. The torque which it depends on that will be very high, and the starting torque will be very high. Is it clear? Confirm me. Is it clear? Confirm me. Right. See, today one of the student has asked one question through WhatsApp. Sir, you told that the starting torque is directly proportional to resistance. As the resistance is very less, the starting torque is less. And you told that during running, the torque will increase. Sir, when resistance is constant, how the torque will increase during running? Already I told you yesterday, right? Till yesterday, I told you to use that formula. Starting torque is directly proportional to R2. But I told you that what is the main reason for low starting torque and what is the reason for high good running torque. This was already explained. And once again, I made explain today. Right? Is it clear? Confirm, all of you. Right. Done. Right. Now, what is that observation you can see from this? So this electromagnetic torque depends upon two parameters. What are those two parameters? The rotor power in watts at synchronous speed. At synchronous speed. As electromagnetic torque depends upon the rotor input in watts at synchronous speed, so that is the reason we can represent this electromagnetic torque in synchronous watts also. In synchronous watts also, right? So can I say the electromagnetic torque? Don't worry, just I'll come. Electromagnetic torque depends on the rotor input. The rotor input in watts at synchronous speed. At synchronous speeds. Therefore, we can represent the electromagnetic torque in synchronous watts. Synchronous watts. Now, the first point to be noted here is synchronous watts are the units of power or the units of torque. The units of torque. First point to be noted. Sir, we have learned that the units of torque is Newton meter, and you are trying to say that the torque can be represented in synchronous watts. So Newton meter and synchronous watts, you are trying to say that the units are for torque. Numerically, these values are same. No. But what is the difference? I'll explain. First of all, How to represent the torque in synchronous watt? Let me tell, right? Please let me tell. If I want to represent the torque in synchronous watt, first of all, you should know the definition for synchronous watts. Definition for synchronous watts. First of all, you should know the definition for synchronous watts. Sir, what is the meaning of definition? I'll tell. See, I'll ask one question. I'll ask one question. I'm having a conductor of unknown resistance. Conductor. So when I'm applying a voltage of say 10 volts across this conductor, it is resulting in some 5 amperes of current. If I ask what is the value of that unknown resistance of that conductor, means your answer will be how much? Your answer will be 10 volts and 5 amperes. What is your answer? Type 2 ohms. Absolutely correct. 2 ohms. There is no doubt in that. Absolutely correct. 2 ohms. But if I ask why 2 ohms? Why 2 ohms? No answer. You may say Ohm's law, but there is no answer properly. If anyone anyone want to answer, can you please tell why 2 ohms? Don't say R is equal to V by I. As V is equal to 10, I is equal to 5, 10 by 5, 2 amps. Don't say like that. What is the true reason for the 2 ohms? Can anyone tell? What is the true reason for 2 ohms? That is the reason you should be strong in circuits. Unless and until you are strong in circuits, you cannot learn the subject. Why it is 2 ohms? I told it is not Ohm's law. Of course, you can use that Ohm's law to calculate R is equal to V by I. But still, voltage drop, still equivalent power dissipation, current is limited. J sigma E. Okay, current density you want to talk. Resistance offered to 10 ohm because resistor itself absorb power due to mobility. Oh, property of a material. Oh, still opposition to current. Okay, still opposition to current. Still due to resistive nature of the conductor. Okay, fine. Voltage required to pass one current. Yes. So answer I got somewhere, but not full. I'll tell you, right? Please listen. So if I'm correct, so your ohm might have given the definition for ohm. Definition for ohm. What is the definition for ohms? Means if a 1 volt is resulting in 1 ampere of current, then that conductor should have a current of a resistance of 1 ohm. So this is a definition of your ohms, right? So this was tested practically and this was given by your Simon Ohms, the physicist and a mathematician George Simon Ohms during 1825. He made this definition. What is the definition for 1 ohm or ohm? Means if I apply 1 volt across a conductor and if it is resulting in 1 ampere of current, then we can say that conductor can have a resistance of 1 ohms. If the definition is correct, it was already proved, it was already demonstrated by Simon Ohms, and basing on that, he has given the definition for ohms. When a 1 volt is resulting in 1 ampere of current, when the conductor resistance is 1 ohm, then with respect to that, if it is having a current of 5 amperes, when a voltage of 10 volts is applied, then this conductor should have a resistance of 2 ohms. So when that definition is correct, so this answer is correct, and that was already proved by Simon Ohms, then this is also correct. So with respect to the definition of ohms, what is the definition for ohms? If a 1 volt is resulting in 1 ampere of current, then that conductor should have a 1 ohm resistance. So with respect to that definition, so the answer for this is 2 ohms is correct. Is it clear? Confirm me. Is it clear? Confirm me, all of you. So like that, your Henry has given the definition for Henry Farad. So you go through that, right? So please try to learn all this. Similarly, what is the definition for synchronous watts? See, I'm having an induction motor, stator, and this one is a rotor. And from stator to rotor, a power of 1 watt is coming from stator to rotor, a power of 1 watt is coming when the field is rotating at synchronous speed, then I can say this machine is developing a torque of 1 synchronous watts. 1 synchronous watts. So can I say a 3-phase induction motor is said to have developed 1 synchronous watt of torque if a power of 1 watt is coming from stator to rotor when the field is rotating with synchronous speeds, right? So what is the definition for synchronous watt? Means a 3-phase induction motor is said to have developed 1 synchronous watt of torque, 1 synchronous watt of torque if a power of 1 watt is coming from stator to rotor, nothing but the rotor input, from stator to rotor, at synchronous speed, right? So nothing but the rotor input power in watts is nothing but your torque in synchronous watt, right? So a 3-phase induction motor is said to have developed 1 synchronous watt of torque if a power of 1 watt is coming from stator to rotor at synchronous speed. So this is the definition for which one? Synchronous watts. Just like your ohms, if a 1 volt, if it is resulting in 1 ampere of current, that conductor should have a resistance of 1 ohm. Then similarly, if a motor is having 1 watt of rotor input power when the field is rotating with synchronous speed, then we can say that the motor is developing a torque of 1 synchronous watt. Is it clear? Is it clear? Right. What happened? Only few, nearly 300 plus are there. I can see only 60, 70. What about others? All of you raise your hands. Raise your hands. Right, done. Now I'll answer. What is the torque in Newton meter and torque in synchronous watt? Both are same or different? We'll see. We'll see. We'll see. So already you have taken one example in that power stages. What is that example? The stator input power is equal to 40 kilowatts. The stator losses are 2 kilowatts. Then the rotor input, nothing but the stator output is equal to stator input minus stator losses. So this is equal to 38 kilowatts. How many pole machine it is? 6 pole. If you recall, the supply frequency is 50 hertz and the speed is 1000 rpm. Now I want to represent the torque in electromagnetic torque in Newton meters. So what is the formula for that? The rotor input by omega s. So what is the rotor input? 38 into 10 power 3 by omega s, 2 pi 1000 by 60. So it is 363 Newton meter. 363 Newton meter. So this is the torque in Newton meter. I want to represent the torque in synchronous watt. Then you can see if 1 watt is coming to the rotor, how much torque is developing? 1 synchronous watt. But how much power is coming to the rotor in this case? 38,000 watts of power is coming to the rotor. Then how much torque it will develop means in Newton meters. So it will develop 38,000 synchronous watts of torque it develop. So this is nothing but your rotor input power. So that is the reason tomorrow in your examination, if the same question is asked, the torque is dash. If the units on the right hand side is Newton meter, then you have to answer 363. If the units are in synchronous watt, you have to answer 38,000. But if you are not looking into the unit, then your answer will go. So that is the reason tomorrow in your gate examination or anything, you have to be careful with the units given. So with respect to that units, you have to answer the question. So what is the answer for this is 38,000 synchronous watts, right? I hope this point is clear. Confirm me all of you. Right. So So if anyone asks, is it possible to represent the torque in synchronous watts? Yes. So first, tomorrow in the interview, if the question is asked, are the synchronous watts is the units of power or torque? The units of torque. What is the difference? You have to explain all these things, right? So this is something about your torque in synchronous watts. Now let us go for the equation. So electromagnetic torque is equal to 1 by omega s into the rotor input. So please remember one thing in your brain, that is we are finding out the performance parameter using rotor equivalent circuit. So whatever the equations we are supposed to derive or should have should be in terms of the rotor equivalent circuit. So what is the equation for the rotor input power? It is 3 I2 square into R2 by S, right? I'll substitute this here. So if I do that, so electromagnetic torque is equal to 3 by omega s into I2 square into R2 by S. So this is the equation for the electromagnetic torque, right? So this we call it as basic torque equation. Basic torque equation. Basic torque equation, right? I hope this is clear. Confirm me all of you. Right. Still I can simplify that. How? So electromagnetic torque is equal to 3 by, in place of omega s, I write 2 pi ns by 60 into I2 square into R2 by S. So this will be electromagnetic torque is equal to 180 by 2 pi ns into I2 square into R2 by S. So this is something about the definition for the electromagnetic torque. So if anyone questions you as of now, do you have any formula to calculate the rotor input power? Yes, 3 I2 square into R2 by S. Any formula you have to calculate the rotor losses? I2 square into R2. Any formula you are having to calculate the gross mechanical power developed or the internal mechanical power developed? Yes, 3 I2 square into R2 into 1 by S minus 1. Do you have any formula to calculate the magnitude of that electromagnetic torque? Yes, 180 by 2 pi n s into I2 square into R2 by S. So if the question is like this, I'm having a three-phase induction motor and that induction motor is in New Delhi. As of now, I know only the rotor circuit parameters. What is that? E2 naught I know, R2 I know, X2 naught I know. And I want to calculate the rotor input power, the rotor losses, the gross mechanical power developed, right? And the electromagnetic torque when the machine is operating at a slip of 4%. Can I find out? Yes. So here, please see, I'm trying to link up, please see. I'm having an induction motor. I'm having an induction motor. And with respect to induction motor, what are the things available with me? E2 naught is available. R2 is available. X2 naught is available. So these are the equivalent circuit parameters. If you recall yesterday, these are available. E2 naught, R2, X2 naught is available. Now you want to calculate if the motor is operating at a given slip, what is the value of I2, what is the value of rotor input, what is the value of rotor losses, what is the value of rotor output power, what is the value of electromagnetic torque. Can you find out? Yes. Why? Because I have the formula E2 naught by square root of R2 by S whole square plus X2 naught whole square. Like that, you can calculate this, you can calculate this, you can calculate this, you can calculate this. So as of now, if I know the rotor equivalent circuit parameters, what are those? E2 naught, R2, X2 naught. If I know these three parameters, I can calculate input power, rotor input, rotor losses, rotor output when the motor is operating at a given slip. I can find out all these things, all these things. Is it clear? Is it clear? Right. So generally how the problems will be given. I'm trying to give the basic logic. So this logic you can use for calculating any problem. So what is that given means? Generally a three phase 400 volts is given. Poles, 6 poles, 50 hertz are given, right? Something is given and R2 is given and X2 not are given. So E2 not is not given. There are two possibilities for E2 not. E2 not may be given directly, or it may be given indirect. Given directly, or it can be given indirectly. When how it is given indirectly, like the supply voltage is given. So this is a line voltage. Assuming that the windings are connected in star, so it is 400 by root 3, right? You will get some value. And stator to rotor turns ratio will be given. We'll see that will be given. And from that, as the stator impedance is not given, E1 is equal to V. And from that, you can calculate E2 naught is equal to E1 by A. What is that? We'll see that, right? So from that, like we can calculate. So can I conclude like this? If the rotor circuit parameters are given R2, X2 naught, E2 naught. So these are the three things which I need to find out all the performance parameters. If E2 naught is given, R2 is given, X2 naught is given for a given slip. For a given slip, slip may be given or speed may be given. For a given slip, I can calculate input, losses, rotor output, the magnitude of electromagnetic. I can calculate all these four parameters if these three parameters are given for that particular motor. Is it clear? All of you confirm? Right. So tomorrow, if you look into any numerical, if the rotor input is given or anything is asked, first you have to look. Only rotor circuit parameters are given, stator circuit parameters are also given. As of now, we don't know anything about stator circuit parameters. Okay, what are the rotor circuit parameters required? R2, X2 naught, E2 naught, right? R2 will be given, X2 naught, E2 naught is given directly. That is the voltage across two slip rings. Like that, there may be some indirect information. E2 naught is given, no. That means the supply voltage may be given. From that, you have to get E2 naught. Once you are having E2 naught, you can calculate all these values. I hope this is clear. Confirm me, all of you. Confirm me, all of you. Right? Anyhow, I'll proceed. So this is something about your which equation? Electromagnetic torque equation. Right? Next one is approximate steady state analysis. Right? Approximate steady state analysis. I'll just, before I take the numericals, then you should have, okay, how to solve the numericals. So if you just remember all these things, you can solve any numerical. Please see. Approximate steady state analysis. So what is this approximate steady state analysis means? Finding out the performance of a three-phase induction motor by considering only the rotor circuit parameters. As of now, we don't know about the stator circuit. Only by considering the rotor circuit parameters, we're finding out the performance parameters, right? So approximate steady state means finding the performance of a three-phase induction motor by considering only the rotor circuit parameters, neglecting the stator circuit parameters. Is it clear? Confirm me. Confirm me. Right. See, Baba. So my suggestion is My suggestion is, please, after this class today, go for Nagaratan Kotari, P.S. Bhimra, Bhattacharya. So electrical machines by Bhattacharya is there. Electrical machines by Chapman. Electrical technology by B.L. Thereja. Right? So you please try to pick up the numericals from power flow, power stages, and this torque calculation. So if you know the content, then if you know the procedure, you can solve all the numericals. I'll give the logic, don't worry. So here, what is that we are neglecting? Stator circuit is neglected. So here, we are neglecting, please see, neglecting Z1. What is that Z1? Stator impedance we are neglecting. Impedance is neglected. When stator impedance is neglected, the drop I1 into Z1 is also neglected. Neglected. In that case, V1 per phase will be equal to E1 per phase. Why? Because the drops are neglected. Then if A is the turns ratio, A is the turns ratio, then you know that E2 naught by E1 is equal to A, right? Sorry, 1 by A. 1 by A, or this is equal to K, right? Then you may have a doubt. Sir, in case of induction motor, we are having two E's. One is E2, the other one is E2 naught. So while I equate, in case of transformer, if you remember, K is equal to E2 by E1. There is only one voltage in the secondary, E2 by E1. There is no doubt in that. So this is nothing but 1 by A also. But in case of an induction motor, we are having two voltages in the rotor circuit. One is the standstill voltage, E2 naught. The second one is the running voltage, E2. So while finding out this ratio K, I need to go for E2 naught by E1 or E2 by E1. Remember, K is a constant. It is a fixed value. So in that fixed value, the voltage, secondary voltage should be fixed. So which one is a fixed voltage here? E2 naught is a fixed voltage. Why? Because E2 is S into E2 naught. So S is a variable. So you cannot take E2. You have to take E2 naught. Or one more thing, you can take like this. The frequency should be same. So what is the frequency in E1? F. What is the frequency in E2 naught also? F. So while you're finding out this ratio, the frequency term in that E1 and the frequency term in E2 naught should be same, right? So what is the frequency term in E1? F. What is the frequency term in E2 naught? F. But if you take E2, it is SF. So that is the reason in this case, K is equal to E2 naught by E1, or this is equal to 1 by A. So here K is the transformation ratio and A is the turns ratio. Turns ratio. So from this, how to calculate E2 naught? So E2 naught is equal to E1 by A, that is equal to V1 by A. Then I'll draw the equivalent circuit. Equivalent circuit. What is the equivalent circuit? When there is no stator, then what is the equation for I2? Right? And I'll substitute this in the basic torque equation. What is the basic torque equation we have? Just hold for 2 minutes. You will understand everything. Just hold for 2 minutes. I2 square into R2 by S. So here it is 180 by 2 pi ns. In place of I2, I write this. Into R2 by S. If I simplify that, 180 by 2 pi ns S E2 naught square into R2 by R2 square plus S X2 naught whole square. This is the equation for torque for the slip ranging from 0 to 1. This I call it as approximate torque equation. Approximate torque equation. Done. Right? Why I'm calling it one as a approximate torque equation means only the rotor circuit parameters are given. See, tomorrow, if anyone want to ask any question on this approximate steady state analysis for calculating the rotor input, for calculating the rotor losses, for calculating the rotor output, for calculating the torque, what is required for us? R2 is required, X2 naught is required, and the slip at which you need to calculate is required. And in addition to this, E2 naught is required. If these four parameters are given, then you can calculate rotor input, you can calculate rotor losses, you can calculate rotor output, and you can calculate the torque at any slip. You can calculate all these things. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. Then what are the possibilities that this E2 naught may be given? This E2 naught may be given directly. May be given directly. What is that? The rotor standstill voltage per phase is equal to 57.7 volts. It is given directly. The other possibility is that this E2 naught may not be given directly, but the voltage across slip rings, are given. Then using that you have to calculate E2 naught. Using that you have to calculate E2 naught. I think this is clear. Confirm me. Confirm me. Right. Third possibility is neither the voltage across the slip rings are given nor E2 naught is given directly. But what is that? Line voltage is given. The stator winding connections are given. The turns ratio is given. In this case, E2 naught is equal to the per phase voltage by A, and per phase voltage is equal to the line voltage by root 3 in case of star, and is equal to VL in case of delta. So these are the three possibilities that E2 naught may be given. Other than that, we don't have any possibility to give in E2 naught. So if anyone want to frame a question, so for E2 naught you have to give the E2 naught is this, the voltage across slip ring is this, the supply voltage is this. So this is the information which he is giving for E2 naught. So R2 will be given directly, no doubt. X2 naught will be given directly, no doubt. And this S may be given directly, or NR may be given. NR is given. So when NR is given, how to calculate slip? NS minus NR by NS. Then you can calculate all parameters as of now. As of now. Is it clear? Confirm me. As of now. Clear? So if anyone questions, I'm updating our induction machine class. If anyone questions, Are you have learned the basic class? Absolutely correct. The concept of rotating magnetic field? Absolutely correct. The constructional details of a three-phase induction motor in detail which is required? Yes. The basic requirement for the torque production, two magnetic fields with the relative speed 0, why the pole should be same? Yes. the types of rotor, their differences, their characteristics, their advantages? Yes. After that, the complete working principle? Yes. Knowing the relative speed between the different fields? Yes. After that, the production of torque? Yes. The concept of load angle? Yes. Can you find out the performance of a three-phase induction motor? Yes. Not directly on the motor from its equivalent circuit? Yes, but conditions apply. Only when the rotor circuit parameters are given, I can find out the performance parameters as of now. So what are the performance parameters you can find out? I can calculate the power which is coming to the rotor, the losses in the rotor, the output of the rotor, the torque developed by the rotor, the efficiency of the rotor. I can find out all these things. So if you want to calculate all these things, what is required? R2, X2 naught, the operating slip at which you need to find out, the E2 naught. So what are the possibilities that E2 naught may be given in any numerical? You search N textbook. The possibility of giving E2 naught is only by three ways. Number one is E2 naught may be given directly, or the voltage across any two slip rings at standstill may be given. The second one is, instead of giving the rotor voltage at standstill, the supply voltage will be given. The turns ratio will be given. From that, you can calculate E2 naught. So these are the three possibilities for E2 naught. And if I want to calculate the performance parameter, I need the slip. The slip may be given directly, or the slip may be given indirectly by with the help of a speed, and you can calculate that. Yes, and you can calculate all the performance parameters. Is it clear? Is it clear? So if I want to waste the time, so I can take the numerical like this. E2 naught is 100 volts, R2 is 0.12, X2 naught is 0.85, slip is 0.04. Calculate the rotor current. Calculate the rotor power. I can do like that, but it is waste of time. But I'm trying to give the flow. I'm trying to give the different concept which are being collected from the different textbook, and you can solve any numerical on this, right? Finally, you raise the hands if it is clear. Confirm me, right? So today you are having more work. You have to solve the numericals from your power stages, and you have to solve the numericals from this. Why? Because I'm giving all the problems which we have covered in all the textbooks. It is 100% true that if you understood this, then you have to answer. Say maximum of maximum, what that fellow can ask in the induction motor, what that fellow can ask. Or I'm having a three-phase induction motor. Okay, rotor resistance is this, reactance is this, it is operating at a slip of this. Calculate the rotor input power. Yes. Gross mechanical power, yes. The electromagnetic torque when the slip is this, yes, I can calculate. I have the formulas, I can calculate, right? Next one is few observations. So that is the reason, first you should know the content and how to apply this content for the formulas, for the problems. You have to see. Anyhow, I'll try to solve one or two numericals. You can understand that. Don't worry. Then you understand, oh, whatever the sir told. So from that only these concepts will come, right? You can see that, right? Observations. Observations with respect to the torque equation. Observations. What is that? I'll take this torque equation. What is the torque equation? 180 by 2 pi ns s E2 naught square into R2 by R2 square plus S X2 naught whole square. So this is the equation for the electromagnetic torque for any value of slip ranging from 0 to 1. Please remember it is an approximate torque equation. Why I'm calling it as an approximate torque equation means you can see you are using only the rotor circuit parameters, right? Rotor circuit parameters, right? So if you look into this torque equation, there are many parameters. What are those? S, E2 naught, R2, like that. I'm going to divide the total parameters into three categories. What are those three categories? See. One is the design parameters. Design parameters. What are those? R2, X2 naught, poles, the star or delta connection, stator to rotor turns ratio. So these are the design parameters. So if you want to vary any of your motor parameters using varying this, so this has to be done only during the design stage. Once the design of motor is over, you cannot change those values. Why? Because the design is over. So if you want to change any of these rotor input, rotor losses, rotor output, so if you want to vary those parameters, that has to be changed during the design stage. If you want to vary by varying these parameters, once the motor is ready, once the design is ready, you cannot vary by varying these parameters, right? The next one is excitation parameters. Excitation parameters. Excitation parameters. So what are those excitation parameters? The supply voltage and frequency. If you're feeding the three-phase excitation from a fixed voltage and fixed frequency source, then we cannot vary the torque by varying these parameters. Why? Because the voltage and frequency are fixed. But very unfortunately, if you are varying, or if you are feeding this from a variable voltage and variable frequency, then by varying these parameters, we can vary the torque, right? Let us see. The next one is the load. So by varying the load, we can vary the speed and we can vary the slip, right? So finally, what I want to tell you now means we are going to see how the motor torque varies, how the electromagnetic torque varies if you vary the motor parameters. So what are those motor parameters? If you are varying the design parameters, how the torque will vary. If you are varying the excitation parameters, how the torque will vary. If you are varying the load parameters, how the torque will vary. We are going to find out these variations, and with respect to torque, we are going to find out. The first thing is what I want to do means the motor is ready. When the motor is ready, we cannot change this. Now what I'm trying to do means I'm trying to vary the supply voltage, keeping the frequency constant. The motor is operating under no load condition. The motor is operating under no load condition, and I want to find out, so with the changes in voltage, how this torque will vary. I need to find out. All the other parameters are kept constant. I need to find out the relationship between the motor torque and the supply voltage if the remaining parameters are kept constant, right? So let us see. If I take electromagnetic torque, it is 180 by 2 pi ns s E2 naught square into R2 by R2 square plus S x2 naught whole square. So here you can see only where voltage is varied. So what are the parameters I'm keeping constant here? Frequency is constant and pole I'm keeping constant. In that case, Ns will remain constant. This will remain constant. We are not changing. Resistance is constant. Leakage reactance is constant. The motor is operating without load, means slip is constant. Then what is the relation we are having? As there is no load, the slip will remain constant. What is the relation? Electromagnetic torque is directly proportional to E2 naught square, and it is E1 by A. A is again constant, E1 square, and it is V1 square. So finally, electromagnetic torque is directly proportional to supply voltage square. Supply voltage square. So what do you mean by that? I'll take one example you can understand. See, after this I'll give break. See, initially I'm applying a voltage of V. Then the electromagnetic torque developed by the motor is say T. So what is the voltage I'm applying initially? V. Then what is the torque developed by the motor? T. Now I'm decreasing this voltage by 10%. 10% means instead of V, I'm applying 0.9 V. So 10% is reduced. So voltage is reduced by 10%. Then what happened to the magnitude of this electromagnetic torque? So electromagnetic torque is directly proportional to V square. So TEM1 by TEM2 is equal to V1 by V2 whole square. From this, TEM2 is equal to V2 by V1 whole square into TEM1. So it is 0.9 into V by V square, V whole square into T. It is 0.1 into T. So what is the percentage change in torque? T minus 0.81 into T by T into 100. So it is 19%. I can approximate it to 20%. So what is the change in voltage from V to 0.9? So what is the change in voltage? It is 10%. So when the voltage is reduced by 10%, the motor torque is reducing by 20%, keeping all other parameters constant. So this question was asked in multiple times in many exams. What is that? The input to a three-phase induction motor is reduced by 10%. Then what is the magnitude of torque? So how much percentage it is reduced? So it is reduced approximately by 20%. 20%. Is this clear? Confirm me. Confirm me, all of you. Right. So we are trying to see some observations just before we give the break, and we are trying to see some observations. What are those observations? If the input to a three-phase induction motor is reduced by 10%, the motor torque reduces approximately by 20%, right? So I can write like this. If, after this I'll give break. If the input voltage of a three-phase induction motor is reduced by 10%, the motor torque reduces approximately by 20%. Don't say 19, approximately 20%. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. Right. So one observation we have seen. So what is the relation we are having between the motor torque and the supply voltage? Means motor torque is directly proportional to the square of the supply voltage. Square of the supply voltage. Whenever the supply voltage is reduced by 10%, then the torque will reduces approximately by 20%. So that is the reason you are never, or you are not supposed to operate the motor with less than the rated voltage. If the rated voltage is say 400, you are applying a 10% voltage less 360, then the torque will be reduced by 20%. You can see such a huge effect is there on the motor torque with the voltage. So that is the reason you should be very much careful while you are applying the voltage to the motor. It should be always the rated voltage which is mentioned on the nameplate details. If you are applying a voltage less than that, then the torque which is supposed to be developed, it is developing less than that value, and the motor may not drive the loads. Why? Because you're applying a reduced voltage. So this is a very, very important thing. From that we can learn. Is this point clear? Confirm me, all of you. Is it clear? Right. So next observations we'll see after the break, right? Please. Right. Thank you. Right, I'm back. Right. So all of you confirming, raise the hands if you can hear me. Right. So what is the first relation we are having between the motor torque and the supply voltage means the motor torque is directly proportional to the square of supply voltage. The next relation is I want to bring the relationship between this motor torque and this slip. That means for the fixed excitation and for a given motor, when the slip is varying from 0 to 1, how the torque will vary. So for a fixed excitation, for a given excitation and for a given motor, with the slip, how the torque will vary. I want to bring the relationship between torque and slip. But if you see this basic torque equation, you can find the slip is present in both numerator as well as in denominator. So for that, what I'm trying to do means I'm trying to divide this into two regions. One is what is the relation we have between torque and slip during low slip operations? What is the relation we are having between torque and slip during high slip operation? So when I'm talking about low slip operation, it should be less than 10%. High slip means more than 10%, right? So what is the first observation we have between torque and voltage for a given motor? Keeping all other parameters constant, if I vary the supply voltage, the electromagnetic torque is directly proportional to the square of supply voltage. Now, for a given excitation and for a given motor, we need to find out the relation between the motor torque and slip. But you can see that slip is present in both numerator as well as in denominator. I'm going to divide into two categories. One is, second point is low slip operations. Low slip operation, this we call it as no load operation also. Why? Because during no load, the speed will be closer to ns. No load operations are lightly loaded conditions or running light conditions. Running light conditions, right? So in all these cases, the rotor speed will be closer to synchronous speed. Then slip will be approximately equal to 0. When slip is approximately equal to 0, you can see R2 by S as it is approximately equal to 0. R2 by S whole square will be much greater than X2 naught square. If that is the case, R2 square is greater than S X2 naught whole square. So can I say during low slip operation, R2 square will be, say, charging 18%, don't worry, up to 10 we can have. R2 square will be much greater than S X2 naught. What do you mean by that? See, I'm having this torque equation 180 by 2 pi ns S E2 naught square into R2 by R2 square plus S X2 naught whole square. So what is the meaning of this R2 square much greater than means? If you are calculating this electromagnetic torque with Sx2 naught whole square without Sx2 naught whole square for low slip operation, the answer will be same. Even if you consider Sx2 naught whole square and calculate the torque, or even if you are not considering Sx2 naught whole square and calculating the torque during low slip operation, there will not be much change. Why? Because that R2 square will be dominating more compared to that Sx2 naught whole square. Is this point clear? Confirm me. Is this point clear? Confirm me, all of you. Right. So here, so electromagnetic torque is equal to 180 by 2 pi ns s E2 naught square into R2 by R2 square. So here you can see 1 R2 gets cancelled. As we are not changing the excitation parameters, this is constant. As we are not changing any voltage, so E2 naught square by R2 will also remain constant. So what is the relation we are having between torque and slip during low slip operation? Torque is directly proportional to slip. So during low slip operation, the electromagnetic torque is directly proportional to slip. So tomorrow if anyone questions you, Are Baba, can you please tell me the relationship between the developed motor torque and the slip? Then you have to question him back. See, it is not possible to bring the relation, but I can tell the relation if you're talking about low slip or high slip. Now you tell me what is the relation we are having between torque and slip during low slip. The relation is directly proportional, right? Is this point clear? Confirm me all of you. Is this point clear? Confirm me all of you. So can I write during low slip operations, low slip operation, the electromagnetic torque is directly proportional to slip. The nature of torque slip characteristics is a straight line. Is a straight line. Straight line. I hope this point is clear. All of you confirm with me. Confirm me. Right. So I want to compare this with a small example, a railway coolie example. So what is the nature of work of a railway coolie? The nature of work of a railway coolie is to carry the luggage, weight. So when there is no load on the head of the railway coolie, then what is that energy he need to spend? He need to spend a small energy so that he can walk without any difficulty. So here also, when the motor is operating without load, then what is the magnitude of torque it is developing? A small. Why? Because when the motor is operating without load, the speed will be closer to ns, the slip will be approximately zero, the motor torque value will be approximately zero, means as there is no load, the required torque to turn the rotor will be very, very less. Now, when you are increasing the load, then to supply the load torque, the motor torque has to increase. So how it is happening? From this equation, I can say whenever the load is increased, the speed is decreased. With the decrease in speed, the slip is increasing. With the increase in slip, the torque is increasing. So with this, it is clear. But truly speaking, what is the mechanism happening inside the machine? So whenever the load is increased, the speed decreases. With the decrease in speed, the relative speed between the field and the rotor conductors will increase. Flux cutting the rotor conductors will increase. Current will increase. I2 will increase. Phi2 will increase. Opposition to the main field will increase. Then phi r will decrease. As a result, E1 decreases. V minus E1 will increase. Current drawn will increase. Power drawn will increase. The power fed to the rotor will increase. The torque which depends on that will increase. So what is the relation we are having means you have to imagine from this point to go back. Again, you have to come back to this point. What is that? Load is increased. Then obviously speed decreases. This was already explained, please. Speed decreases, relative speed increases, flux cuttings increases, EMF in the rotor conductors increases, current increases, phi2 magnitude will increase, opposition will increase, that flux in the air gap will decrease, E1 will decrease, V minus E1 will increase, current drawn will increase, power drawn from the source will increase, power fed to the rotor will increase, the torque which depends on that power will also increase to supply to the load torque. So what is the relation we are having between torque and slip during low slip operation? Directly proportional. Is this point clear? Confirm me all of you. Confirm me all of you. Right. See Baba, I'm not explaining anything on the basis of equations. If someone explain on the basis of equation, it is a foolish thing, right? So your exam, your content will not be basing on the equation you have to analyze. Few things you have to analyze an equation, but everything you have to imagine what is happening inside and you have to analyze. Please remember that. So this is the second point. What is the third point is during high sleep operations, high sleep operations, high sleep operations are fully loaded conditions. Fully loaded conditions. So in this, what happened to the rotor speed? The rotor speed will be little bit away from ns, right? When the rotor speed is little bit away from ns, the slip will increase. When slip increases, R2 by S. When slip increases, R2 by S whole square will start decreasing. Then here, R2 square will be much lesser than S X2 naught whole square. During which operation? High sleep. So can I say during low sleep, the resistive nature is dominating. The resistive nature is dominating, whereas during high sleep, the inductive nature is dominating. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. So once again, during low sleep operation, as the speeds are very closer to ns, the frequencies of the rotor currents will be very, very less. The rotor circuit will be high resistive in nature. High resistive in nature, the power factors will be high and active power drawn will be high. But during high sleep operation, which fellow is dominating here? The reactance part is dominating. You can see on one stage that fellow is dominating, on the other stage this SX2 naught is dominating. So what do you mean by that? So during high sleep operation, if you are calculating the torque, considering R2 square, neglecting R2 square will give the same answer. Why? Because during high sleep, as sleep value is more, S into X2 naught value will be high and the resistance will be less. So during high sleep operation, can I say electromagnetic torque is equal to 180 by 2 pi ns S E2 naught square into R2 by S square into X2 naught square. So here you can see these are all constants and SS will get cancelled. So what is the relation we are having between torque and slip? Inversely proportional. Inversely proportional. During low sleep operation, it is directly proportional, but whereas during high sleep operation, it is inversely proportional. So during high sleep operation, during high sleep operation, electromagnetic torque is inversely proportional to the slip. The nature of torque slip characteristics is a rectangular hyperbola. Rectangular hyperbola. I'll draw that, don't worry. Rectangular hyperbola. I'll take the same railway coolie. See, when there is no weight on the head of that railway coolie, so without any issue, without any difficulty, he can carry the weight. But if you go on increase the load on the head of that railway coolie, a stage will come, so he could not produce the required energy to carry the weight, and that fellow will get collapse. Is this point clear? Confirm me. Confirm me. Similarly, even in case of an induction motor, also when the motor is operating without load, then if you go on increase the load, it is true that up to certain torque, the motor can rotate, it can supply the required load torque. But after a certain torque, that we call it as maximum torque, if you are loading the motor beyond that value, then the motor could not produce the required torque and the motor will stop rotating. It will come to standstill. It is an unstable position. Right? I hope this point is clear. Please confirm me, all of you. Then you may have a doubt, sir, as you said that with the increase in the load, the speed is decreasing. When the speed is decreasing here, the relative speed is increasing. When the relative speed is increasing, fluctuatings are increasing, currents are increasing, the 5 2 magnitude is increasing, then the power drawn is increasing, but the torque should increase now. Very sad thing is, during high slip operation, which fellow is dominating here? The reactance part is dominating. As the reactance part is dominating, during high slip operation, which power will increase means the reactive power drawn from the source will increase, but the active power drawn will start decreasing. Why? Because as the relative speed is increasing, the frequency of the rotor currents are increasing. When the frequencies of the rotor current is increasing, the inductive nature starts increasing. When the inductive nature is increasing, obviously what happened to the power factor of the rotor circuit starts decreasing. Now the machine will draw reactive power than the active power. The rotor receives more reactive power compared to active power. When the machine is receiving more reactive power, less active power, the torque depends upon the active power, and hence the torque will start decreasing. So during high sleep operation, the amount of power fed to the rotor, active power fed to the rotor will start decreasing. Why? Because with the increase in the speed, the frequencies are decreasing, the reactive power drawn from the source will increase, and active power will start decreasing, and hence the torque will decrease. Is this point clear? Confirm me. Once again, I repeat, during low slip operation, which one is dominating here? Resistance part. Rotor circuit is highly resistive, drawing more current, drawing more active power. The torque will be more. But during high slip operation, the motor circuit is highly inductive, drawing high current, but before it is drawing reactive power. But the reactive power will be less, the torque will be less. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. All right. How many relations we are having between torque and slip? Two relations. What is that? During low slip operation, the motor torque is directly proportional to slip. It is a stable operation. On what basis I can say it is a stable operation? With the increase in the mechanical load, the active power drawn from the source is increasing, the active power fed to the rotor is increasing, the torque developed by the motor is increasing to supply the load torque. It is a stable operation. So with that increase, the motor torque is also increasing. But here, during high slip operation, the motor torque is inversely proportional to slip. It is an unstable operation. Why it is unstable operation? With the increase in the mechanical load, the reactive power is increasing. Why? Because the frequencies of the rotor currents are increasing. Reactive power is increasing, means indirectly active power is decreasing. The torque is decreasing. That means when you are increasing the load, the motor is slowing down. A stage will come, the motor will stop. So it is an unstable operation. You imagine a railway coolie. So, oh, very low battery. Just imagine a railway coolie. When the railway coolie is having no weight, light weight, then that person is more stable. He can walk without any difficulty. But if you go on increase the load, heavy load, then that person becomes very unstable. We don't know, at some point that fellow will get collapsed. Here also, if the machine is lightly loaded, then the machine will be stable, so it can supply the required torque. But if the machine is heavily loaded, we don't know at what time it will come to stand still or stopping position. I think this point is clear. Confirm me, all of you. Right. So 1 minute. So 10% that laptop charging. Just I'll put charging. Right. 1 second. So which one is a stable now? Low slip. And which one is unstable now? High slip. Please confirm me, all are there. Confirm me, raise the hands. Right. Then very important point is, fifth point. You know that in case of an induction motor, the electromagnetic torque is due to the interaction of stator and the rotor magnetic field. But for a stable operation, the motor torque should be always equal to load torque. What do you mean by that? See, I'm having a three-phase induction motor and there is no load on the three-phase induction motor. When I try to give a three-phase supply to that induction motor, then it is true that the induction motor will start rotating. Why? As there is no load on the rotor, then the motor has to develop a small amount of torque to compensate that load torque. So it will produce the torque and it will make the rotor to rotate. It is a stable operation. On what basis I can say stable operation? Whatever the torque the load need, the motor is producing the same torque. Both these torques are same, right? And hence the motor is operating in a stable mode. But what I will do means I'll put some 1000 kg weight here. Initially, how much kg weight I'll put? 1000 kg weight I'll put. Then I'll give the same three-phase supply to that motor. In this case, the motor can't rotate. But it doesn't mean that a three-phase induction motor is a non-self-starting motor. Why it is not able to rotate means, so whatever the torque the motor is developing, it is not sufficient to drive the load. So that load need very high torque, but the motor is not able to produce the required torque, and hence it is unstable. It is not rotating. So on what basis I can say the motor is operating stably at every speed, at every condition means if it is able to produce the required torque demanded by the load, then it is, I can say it is stable. If not, it is unstable. A small example, you take a middle class family. So if they are able to earn the money which is required for that household needs for a month, then they are stable. But if they are not able to earn the required money for a month, then they will be unstable. The same is the logic here. If the motor is not able to produce the required torque to drive the load, then it cannot rotate. It is unstable. If it is able to produce the required torque to drive the load, then it is stable. Is this point clear? Confirm me. Confirm me. Right. So can I say a three-phase induction motor develops the electromagnetic torque due to the interaction of stator magnetic field and rotor magnetic field, right? Right, it is true. Then if electromagnetic torque is equal to the load torque, then I can say it is stable. If the electromagnetic torque is not equal to the load torque, it is unstable. It is unstable. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. Right. The last point is every motor will have a maximum torque. That means it is the highest torque the motor can produce. If you are loading the motor beyond this torque, the motor will stop rotating, right? So if T max, T suffix max is the maximum torque and TL is the load torque, then if TL is less than T max, applied load is less than maximum, stable. If TL is greater than T max, it is unstable. Unstable operation. I hope this point is clear. All of you confirm me? Confirm me, right? So these are some observations what we are having with respect to the rotor circuit, right? Now the question is, please see how to link up. Or if the rotor circuit parameters are given, what are those rotor circuit parameters? R2, X2 naught, E2 naught are given, and when the motor is operating at a particular slip, yes, you can calculate the rotor input, you can calculate the rotor losses, you can calculate the rotor output power, you can calculate the torque at that particular slip. So can you find out all these things? Please confirm me. Can you find out? Yes, you can find out all these things. Now I need to find out some particular torques from which we define their performances. What are those particular torques? One is the full load torque, the other one is the starting torque, the other one is the maximum torque. Like that, we need to find out some performance parameters in addition to that what we have discussed. That is rotor input, rotor losses. In addition to that, we are going to find out some more performance torques, right? Some performance parameters. What are those some performance parameters we are going to find out? Some more. Already we have seen some. What are those some? Rotor input, rotor losses. We have seen some more performance parameters. Can you calculate rotor efficiency? Yes. I know rotor input is equal to 3I2 square into R2 by S. Rotor output is equal to 3I2 square into R2 into 1 by S minus 1. From that, I can calculate rotor efficiency. As of now, I can calculate rotor efficiency, right? Please. So first one is, what is the first performance parameter? Additional, you are calculating full load torque, or rated torque, right? So we represent this full load torque with suffix T suffix FL. So before I use the equation to calculate the full load torque, what is full load torque definition? So can anyone tell me the definition for full load torque? Full load torque. Stability means running stably. Remember, stability means the motor has to run stably. If it is not running stably, so it is unstable. Maximum slip occurs. Right. Next. Rated current and rated voltage. Full load condition. Right. Anyhow, rated current. Very good. Rated. Anyhow, I'll explain. Just enough. Don't throw enough. See. I'm a manufacturer and I'm designing this machine with respect to some voltage specification and current specifications. And I'm selling this machine in the market. So you are purchasing this machine. So indirectly what I need to do means I need to communicate something to you, right? Unless and until I communicate something to you, you cannot use that machine properly. That means I should tell what is the voltage I need to apply, what is the current you need to supply, what is the supply you have to give, single phase or three phase, how many pole machine, like that. I need to give some information to you indirectly. So some information will be provided on the nameplate details and some information will be provided on the data sheets, right? So why? Because you don't know who is the manufacturer and you don't know the operating manual, you don't know the excitation parameters, you don't know anything. So that has to be provided to the user, right? So via a nameplate details, via the data sheet. I think you understood the importance of a nameplate detail. What the nameplate detail means? The manufacturer you have not seen. He is an unseen fellow. but he's designing that machine basing on something, and he want to communicate to you, right? While you are using that motor, you have to follow this strictly, otherwise the machine performance will come down. I hope you understood the importance of nameplate details. Tell me, all of you, clear? Right. See, what I'm trying to do means I'm trying to design an induction motor, and this induction motor is designed for a voltage V and for a current I. Voltage V and for a current I. See, basing on this power factor of the motor, then that active power drawn will be there, and basing on that, it will be giving the mechanical power. For example, say, I want to design an induction motor which can give a mechanical power equivalent to 5 kilowatts of electrical power. That is my intention. So how much mechanical power we need to design, or for how much mechanical power this machine has to design means I have to produce a mechanical power which is equivalent to 5 kilowatts of electrical power. So that amount of mechanical power I need to produce. So what should be the output mechanical power? 5 kilowatts. Is this point clear? Confirm me. Confirm me. Right? For that, let me assume that I have to apply some 8000 VA. When I'm applying some 8000 VA, after the losses in the circuit, it can supply the power equal to 5 kilowatts. So how to divide that 8000 VA means, so I'll be dividing like this. See, 420 amperes. So when I'm applying a voltage of 400, and when the windings are carrying a current of 20 amperes, then this particular motor is tested to give a output mechanical power equivalent to 5 kilowatts. So this is the design parameters. Then if you look into the nameplate details of the three-phase induction motor, so there will be a voltage rating 400 volts, okay. There will be a current rating 20 amperes, okay. And there will be output power rating 5 kilowatts. What is the meaning of that? And power factor is also there. What is the meaning of that? When you are applying a voltage of 400 volts, and when the windings are carrying a current of 20 amperes, and this machine will operate with a power factor of this much, and this machine can give a output mechanical power of this much. So this is the meaning of that nameplate detail. Is this point clear? Confirm me, all of you. Confirm me, all of you. Right. Now if I want to apply how much voltage in this particular case, 400 volts and 20 amperes. If you remember, we place the conductors in the slots. We place the conductors in the slots, and these conductors are insulated each other, and these conductors should be insulated from the core, and they are insulated each other. So whatever that insulation coating thickness I should have, that insulation coating should have the capacity to withstand a voltage of 400 volts. So basing on that, I'll coat the insulation coating. Then this 400 volts, I'll mention on the nameplate details. What is the nameplate details? My dear customer, my dear end user, please see that you are not applying a voltage more than 400 volts. The reason is, if you are applying a voltage more than 400 volts, whatever that insulation coating I had on the conductor, that insulation coating may not be in a position to withstand such high voltages more than 400, then there will be a flashover occurs. Flashover occurs. Because of this flashover, that insulation damages, conductor shorted, core and conductor shorted, the machine will get a damage, right? So please remember that when you are using this motor, don't apply a voltage more than 400. The reason is the coated thickness, the insulation thickness has a capacity to withstand a voltage up to 400 volts. If you are applying a voltage more than 400 volts, then obviously that windings will get damaged. It is a warning to you, don't apply voltage more than 400. Is this point clear? Confirm? Right. The second thing is 20 amperes. So if I want to get 5 kilowatts of mechanical power, then it is true that I need to see that winding should carry a current of 20 amperes. Then for carrying a 20 amperes, I'll design that conductor. Then what I will do means I'll pass the 20 amperes current in the conductor. Basing on the resistance of that winding, I'll measure the temperature of that. Whenever the conductor carries a current, it will produce heat. Because of that heat, there is a temperature. I'll measure the temperatures and accordingly, I'll take the type of insulation, class A, class B, class C, whatever it may be. Say with a 20 amperes of current, the temperature is 50 degrees, say 50 degrees. Then whatever that insulation I'm using as a coating, that insulation should have a capacity to withstand the temperatures up to 50 degrees. Then I'll mention the same 20 amperes on the nameplate details. My dear customer, my dear end user, please see that you are not loading the windings with the currents more than 20 amperes. If you are loading the windings more than 20 amperes, then the temperatures with that more than 20 amperes will be more. That insulation will start melting, and obviously a stage will come that windings will get damaged. So be careful and try to see that you are not supposed to load the motor with the windings carrying more than 20 amperes. That is the indirect warning to you people. Is this point clear? Confirm me. So finally, can I say like that? If I have designed an induction motor, if I'm applying a voltage of 400 between the lines, if I load the windings with a 20 amperes current, then definitely the machine can give a mechanical power equivalent to 5 kilowatts. 5 kilowatts. So to produce a output mechanical power, the motor needs a torque, turning effect. So whatever the torque the motor develops with a rated voltage and rated current while delivering the rated output power with a rated speed. We call it as a full load torque. Full load torque, right? So with a rated voltage, rated current, rated torque is nothing but your rated torque. Is this point clear? Confirm me. Confirm me. Right. So you can see this is the torque for any value of slip ranging from 0 to 1. This is the torque ranging from 0 to 1. But I don't want that torque. I need a torque at a particular slip when the windings are carrying a rated current. So whatever the torque the motor develops with a rated voltage and rated current while delivering the rated output rotating with the rated speed, we call it as a rated torque, right? So rated torque means the input voltage should be always rated, the input current should be always rated, and the output power should be rated, right? So how means, see, I'm giving 400 volts. There is no load on the motor. When there is no load on the motor, the windings will draw very small current. You know why? Relative speed will be less, everything you know that. But when you start loading the motor, the current drawn from the supply will increase. Like that, you start loading the motor. Like that, the current drawn from the supply is increasing. A stage has come, the windings are carrying the rated current, that is 20 amperes in this case. So with that rated voltage, with that rated current, the developed torque is nothing but electromagnetic torque. So can I say full load torque is nothing but one value of torque in the range 0 to 1. One value of torque in the range 0 to 1. One value of torque in the range 0 to 1 when the windings are carrying rated current with rated voltage. It is one value in the range 0 to 1 when the windings are carrying rated current with rated voltage. Is this point clear? Confirm me. Confirm me, all of you. So can I say full load torque is nothing but electromagnetic torque when the applied voltage is rated, when the currents are rated, when the slip is rated, and when the speed is also rated. So I'm writing it as full load, right? So what is the equation for full load torque? So in place of that, yes, I have to write SFL. So full load torque is equal to 180 by 2 pi ns SFL E2 naught square into R2 by R2 square plus SFL x2 naught square. So this is the equation for full load torque. What is the definition? So can I write? It is the torque developed by the motor. It is the torque developed by the motor. Developed by the motor. By the motor. With rated voltage. Rated voltage. And rated current. While delivering the rated output power. Is this point clear? Confirm me, all of you. Is this point clear? Confirm me, all of you. Only few. What happened to others? So I'll give one question. Let me see how many of you will answer, right? It is a homework. Many times I told you, if you want to calculate torque, the equivalent circuit parameters will be given R2, X2 naught, S, and E2 naught may be given in different ways. You have to try to solve. Please see. Please do it as a homework. So it is a common data, and using this we'll solve the other problems also. Common data. A three-phase 240 volts 50 hertz 6 poles star connected induction motor has the standstill rotor leakage impedance of 0.12 plus j 0.85 ohms per phase. 0.12 plus j 0.85 ohms per phase, right? Stator to rotor turns ratio is 1.8, right? Calculate the full load torque. If the full load slip is 4%. 4%. Do it as a homework. Tomorrow we'll see the answer for this, right? I'll stop for today because we have to spend time on doubts also, right? Just let me get that earphones. Just 1 second. Right. First, let me check any questions here. After that, we can go for the hand raise. Maximum torque occur full rating. No, maximum torque is different from the full load torque. That we'll see tomorrow, right? Don't worry. Torque to produce maximum torque. No, they are different. SFL is equal to 1. It is a starting torque. No. Sir, can you please share the question? Ha, Baba, I'll share. Don't worry. So it is my duty. When I said something, I'll do it. Absolutely no issue. I'll share the questions. See, sir, please tell the names of the book, right? So tomorrow, just I'll share that books. This front pages also can see. Sir, in transformer, we have the turns ratio because of the same core. Have two winding primary, but induction motor turns ratio came. How turns ratio? See, in case of transformer, it is true that you'll be having primary winding and secondary winding, right? But whereas in case of your induction motor, whenever I talk about the turns ratio, remember it is only for your slip ring induction motor. Why? Because only in case of slip ring induction motor, we have the stator turns and rotor turns. In all our calculations, we have to imagine that whatever the motor we are talking is a slip ring induction motor. Only in that case, you'll be having the turns ratio. I hope it is clear. Imtiaz Pasha. Net power is the rotor output power or the rotor input power. See, net power is the shaft power. So when I'm talking about the net power in induction motor, it is the shaft power. Shaft power means it is the rotor output power minus mechanical losses. Please try to refer my yesterday's class. I told you that net power or shaft power is the rotor output, that is internal power minus mechanical losses. Please see. 240 volts means single phase supply in a sir. See, I told you that. See 240. So this is the twist here. In the numerical, the only twist is 240 volts. See, most of the people feel that the 240 volts is a phase voltage and you start working. No. The answer is whenever the terminology three phase is given, remember that three phase means the given voltage is a line voltage unless and until specified it is a line voltage. So in this case, you have to take the 240 as a line voltage. Say tomorrow in some examination, a three phase at 10 volts. So what is the meaning of the 10 volts? It is again a line voltage. So that is the only twist in this question. So most of the people feel that looking into the magnitude of the 240, they take it as a phase voltage. No, you have to take it as a line voltage and proceed. Why? Because the nameplate detail which we see on the nameplate values is always a line value. Please, that is the only difference. So during high slip value, is it x2 not or just x2? See, Baba, see, you don't confuse x2 not at x2. High slip, when the motor is at standstill, that slip is 1, the value is x2 not. During high slip value, it is s into x2 not. So during high slip, that s will be approximately equal to 1, then the value will be closer to x2 naught, but it cannot be x2 naught. So x2 is equal to x2 naught when s is equal to 1. For all other slips, the values may be varying. Please see. If the power factor is given on the nameplate detail, it is a full load. Yes, whatever the data that is given, it is always full load. Please remember. See, there is no need to get the speed and torque relation. Simple. Whenever you are increasing the load, see already I wrote yesterday, speed decreases, relative speed increases, flux cuttings increases, EMF increases, current increases, power increases, the torque will increase. Please remember. Right. So the questions are over. So let us go for this hand raise. Yes, Sirisha B. Sirisha B. You are there? Sirisha B. She's not there. Sai Charan Reddy.
Hello, sir.
Yeah, Baba, please. Sai Charan Reddy.
Sir, if he has full load torque in synchronous watts, then according to the nameplate details given, we can write it directly as a power output, rotor power output, sir.
See, whatever the data that is given in your nameplate details represent the output power. Only that powers will be given. No torques will be given. You can calculate the corresponding torque. You cannot find out or you cannot take it. Understood?
If he asks in synchronous watts, sir,
See,
synchronous watts.
what is your question? Tell me clearly. I'll give the answer for that.
Sir, he is asking full load torque, and if he full load torque in synchronous watts, he is asking, sir.
Okay, so your requirement is you need to calculate the full load torque in synchronous watt, correct?
Yes, sir.
What is the data given?
Data given is he gave power factor, and he gave this value, sir.
Voltage, current he has given.
Rated voltage, rated current. Yes, sir.
But stator losses he has not given. It has to be given now.
Sir, up to now we did not take that stator losses, no, sir. That's
Yeah.
why.
But stator losses are required, right? Okay.
Okay, sir.
See, if only voltage and currents are given, then you calculate what is the stator output at full load. What is the stator output at full load? Stator input at full load minus stator losses. How to calculate the stator input at full load? 3 V phase I full load into cos full load, that is power factor at full load. You'll get the stator input at full load. Is it clear?
Yes, sir. Yes, sir.
Minus the stator losses has to be provided. If you subtract the stator losses, then you will get the stator output or the rotor input at full load. Is it clear?
Yes, sir. Yes, sir.
Then if your question is, if you want to calculate the full load torque in synchronous watt, whatever the stator output you have, it is nothing but the rotor input, and that is nothing but your full load torque in synchronous watt. Is it clear, Sai Charan Reddy?
Yes, yes, sir. Understood.
Right, clear?
Yes, sir. Clear.
Right, Baba. Right, Kumar.
Sir, good evening, sir.
Good evening, Kumar. Please.
Sir, here V2 not by V1 is turns ratio, sir.
So no, it is K. Secondary voltage to the primary voltage is K. Primary voltage to secondary voltage is A. Understood?
Okay, okay. Turns ratio means which one we take, sir? A
Yeah.
or K?
No, it is A. N1 by N2 is turns ratio.
N1 by N2, sir.
Huh.
Okay, sir.
Right.
Thanks.
Right. Imtiaz Pasha.
Good evening, sir.
Good evening.
Sir, the motor rating is 400 volts, 20 amps, 0.8 power factor.
Mhm.
At that time, we can get na stator input 400 into 20 into 0.8.
Yeah, it is a stator input at full load. Correct.
Okay. Sir, if we gave 10 HP like that, it is output also, no, sir?
It is exactly output. So unless and until specified, 10 HP means output power. Understood?
Yes, sir.
If it is given like input, then it is input power. So you can get that input also. Understood?
Yes, sir. Sir, in scroll induction motor, why we not using the turns ratio, sir?
See, in case of squirrel gauge induction motor, do you have any windings?
No, it's a bar.
Bar. So that's the reason there is no question of turns ratio.
Okay, sir. Sir, just a clarification.
Yeah,
In scroll induction motor, the rotor is delta connection, sir.
No. In case of cage rotor, we don't have any windings and other things.
Bars are
Nothing.
short circuited, no, sir.
They are shorted. Only the coils they are shorted. It is not like a question of delta or star. So there is no question of star or delta in case of squirrel gauge. It is only in case of your slip ring. We can talk about squirrel gauge. Star or delta in test.
Okay, sir.
Hmm?
Sir, in scroll condition mode, scroll condition motion, there is a end ring. No, sir. Could you tell me what is that end rings?
End rings in nothing but which provides a closed path. So you are having one bar here, and opposite you are having one bar. So it has to be shorted. So I'll be providing a entering here. So via this path, it is providing a closed path.
Okay, sir. Okay, sir.
Understood?
Yes, sir.
So on the other side, you will be having another entering. So the current will flow like this in this closed path. In other conductors, it will flow like this, like this.
Yes, sir. Okay, sir.
Understood? Right.
Yes, sir. Thank you, sir.
Right. Anil.
Hello, sir. Good evening, sir.
Good evening, Anil.
Sir, today we said in second point.
This one second point.
Yes, sir. Today first class.
Just wait. I'm going there.
Okay, sir.
Ah.
Here motor efficiency we write here one point called 1 by s minus 1 plus s.
It is approximate sum.
Yes, sir. How you will going to obtain this value?
See, I told you derivation is not required. I'll told you one example also. It is basing on the numericals which we see. So the value can be approximated. I took one small kid. See, if I ask him to run, so he's walking 4 meters like that. So basing on that, you can guess. So what may be the distance he can travel. Here also, working out n number of numericals, we can approximate the value of efficiency is equal to this much. I told you this point, right? I think you are not there, Anil, during that time. I
Yes, sir. Just now at this time only I'm going to join.
Yeah, so I told you already that point I made it clear during that time.
Okay, sir. Sir, another doubt.
Yeah, you can ask.
Sir, here we will going to say steady state analysis, na? జనరల్లీ స్టడీ స్టేట్ అనాలిసిస్ అంటే రోటార్ మీద మనం చేస్తాం కదా సార్.
రోటార్ మీద కాదమ్మా. స్టడీ స్టేట్ అంటే ఏంటి? ఒక మోటార్ అనేది ఒక స్టడీ స్టేట్ వాల్యూ అంటే ఇప్పుడు ఫర్ ఎగ్జాంపుల్ ఫ్యాన్ వేసావు, ఆ ఫ్యాన్ స్పీడ్ ఒకేసారి స్టేబుల్ అయిపోదు కదా, తిరిగి 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 ఒక స్టేజ్కి వచ్చిన తర్వాత స్టేబుల్ అవుద్ది, అవునా?
అవును సార్. ఎస్ సార్.
అది స్టేబుల్ అయిన తర్వాత అంటే అంత స్టేబుల్ అయినప్పుడు ఎంత పవర్ డ్రా చేస్తుంది, ఎంత కరెంట్ డ్రా చేస్తుంది, హౌ మచ్ పవర్ ఇట్ ఈస్ డ్రాయింగ్, హౌ మచ్ కరెంట్ ఇట్ ఈస్ డ్రాయింగ్, వాట్ ఈస్ ద టార్క్ ఇట్ ఈస్ డెవలపింగ్, యూఆర్ ఫైండింగ్ అవుట్. దట్ ఈస్ అ స్టడీ స్టేట్.
ఓకే సార్. ఓకే సార్. ఐ అండర్స్టూడ్.
రైట్.
థ్యాంక్ యూ.
రైట్. Shiva. Shiva. Baba, your voice is not that much clear, please.
Hello, sir. Can you hear me, sir?
But not that much clear.
Sir, am I audible now?
Yes. Please tell.
Sir, I have a doubt in synchronous watts.
Yeah, ask whatever it may be, you ask.
Yeah, sir, can you go to the page?
Yeah, I'll go to that. You can see.
Sir, you solved one problem with that. I mean, for example.
Yeah, you can see.
Yeah, here. So here in terms, sir, and let me just explain. Just correct me if I'm wrong.
No problem. I'm there to rectify if you're wrong.
Yes, sir. So in terms of synchronous watts, the torque developed here is 38,000 synchronous watts, right, sir?
It is nothing but the rotor input power.
Yes, sir. So the same in terms of Newton meter, the torque developed is 363 Newton meter.
Yeah, by omega s you have to do.
Yes, sir. So the only difference is the units that we are making the change.
And numerical also. If you are representing in Newton meters, the value will be something. If you are representing in synchronous watt, the value will be something.
Okay, sir.
Understood?
Yes, sir.
Right.
Yes, sir. Thank you.
Right. Right. No one is raising the hands. So I'll stop for today. Someone has raised. Bhavani. Please, Bhavani. Bhavani. Bhavani.
Sir, in excitation parameters, why you are taking only no load condition, sir?
I told you that when you are talking the torque with respect to one parameter, the other parameter should remain constant. For example, if it is not no load, then when you are wearing the load, what happened to slip?
Will differs.
Varies, correct? When it differs, I cannot take that slip as constant in that case. Understood? That is the reason I am assuming that when I am talking about the voltage changes, I am taking that slip is constant here. In that case, that is true.
But slip is also constant at full load, na sir. Why can't you take it full load?
Then, sir, say if it is at full load, then the motor is operating at full load, the slip is constant. Then when you are varying the voltage, then with respect to that full load torque, the torque will vary. For example, the no load torque is say 100 Newton meters. Assume that. When you are applying a voltage of 400, assume that. When you are decreasing the voltage by 10%, then obviously from 100 Newton meter, the torque will be reduced to 80 Newton meters.
Yes.
But when I'm talking about full load torque, the full load torque will be something like say 200 Newton meter. Then when you're decreasing the voltage by 10%, then the torque will reduces to 160 Newton meters.
Yes.
That means that slip is constant there. Understood? So even it may be no load or full load, whatever it may be, the slip should be constant there. Understood?
Yes, sir. Understood.
Right.
That's it, sir.
Right.
Thank you, sir.
Right. Right. So no one is raising. Abdul Rahman. Abdul Rahman.
हेलो
Yeah, Abdul Rahman.
सर मेरा डाउट है जनरल डाउट है सर मेरा
Yeah, you can ask whatever the doubt it may be.
सर अभी एक इंडक्शन मोटर है सर एक वाइंडिंग मैं एक प्रैक्टिकल बोल रहा हूँ मैं एक दुकान के पास से एक इंडक्शन मोटर आया था ठीक है
ओके
उसका स्टार्टर को स्टार्टर फ्रेम ऑलरेडी एग्जिस्टेड है
ओके
उसमें क्या है तो वाइंडिंग खराब होने की वजह से नया वाइंडिंग प्लेस करके वैसा रख दिए ठीक है सर
ओके
लेकिन जो रखते से टाइम पे 3 फेजेस डिवाइड करके चेक करके कौन सा फेज में प्रॉब्लम है कि वो नया वाला से रिप्लेस करे
ओके करेक्ट
हाँ मेरा डाउट क्या है कहते सर जो हमें 3 फेजेस का वाइंडिंग अलग करके कैसा रिप्लेस करना है कि वो तो सर्किल एंटायर सर्किल मैकेनिकल डिग्रीज में रहता 360 राइट सर
यू हैव टू टेक इट इन इलेक्ट्रिकल फाइनली
हाँ कैसा हमें प्लेस करना है वो मेरा डाउट है
बेसिंग ऑन द नंबर ऑफ पोल्स यू आर डिजाइनिंग
सर
नंबर ऑफ पोल्स फॉर हाउ मेनी पोल्स यू आर डिजाइनिंग यू आर सपोज्ड टू प्लेस
फोर वो नेम प्लेट में डेटा रहता ना सर उसमें 4 का तो स्पीड है फिर भी यानी फ्रीक्वेंसी के हिसाब से देखे तो 4 पोल्स का को पता चला मेरे को
या देन यू टेक द रिलेशन थीटा इलेक्ट्रिकल इज इक्वल टू p/2 into थीटा मैकेनिकल अकॉर्डिंगली यू हैव टू प्लेस
अच्छा ये इंडक्शन मोटर को नहीं जो कौन सा भी मोटर हो कौन सा मशीन हो ऐसा ही रहता ना सर
it is induction and synchronous why because the stators of both the machines will be more or less same you have to place like that but whenever you talk about the winding it has to be always electrical degrees
अच्छा अच्छा
understood
वो हिसाब से हम प्लेस करना सर फॉर एग्जांपल दूसरे मशीन है तो उसका बिहेव कैसा रहता सर
it depends upon the poles number of poles
नहीं एसी मशीन से ले लो सर फॉर एग्जांपल कुछ अलग मशीन ले लो आप इंडक्शन मोटर के बारे में बोलते हो को आप ऐसा रिलेट कर रहे हैं सिंक्रोनस का और इंडक्शन का फॉर एग्जांपल दूसरा का कौन सा भी एक मोटर ऐसा हुआ तो कैसा कर सकते हो वो मेरा डाउट था.
See, कैसा करता करता, what I didn't get you. You mean to say with respect to windings?
हाँ, कैसा प्लेस करते हैं सर, वही है.
See,
ठीक है, तो अपन बोल सकते हैं इलेक्ट्रिकल में ऐसा 120 डिग्रीज 360 by m करके ऐसा आता है तो बोल सकते हैं.
only in case of 3 phase we have that issue, but when you're talking about single phase you don't have that issue. So the conductors are distributed in 1 layer, 2 layers, right? Your synchronous machine teacher will explain all those, right? One single layer winding, 2 layer winding, integral slot winding. So all those your teacher will explain in your synchronous machine. So you can learn there. Understood, Rahman sir?
अच्छा अच्छा, ओके ओके सर, ओके, थैंक यू सर. सर और एक आखिरी बात सर, ये आप बोले था कल क्लास नहीं है, कब बोले था?
Tomorrow
जी
for the batch which was started on July 5th, for them
जी
there is no induction machine class.
जी जी.
But for the other batches, so they'll be having power system faults and stability class.
कौन सा टाइम में सर, कुछ पता है सर आपको?
Same 5 to 9.
अच्छा 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 अच्छा.
Same timing, right? Whatever the timings I had, the same timing you'll have.
अच्छा
Okay.
अच्छा अच्छा, ओके ओके, थैंक यू सर.
Right, Rohit. Rohit. Rohit, AP.
Sir,
हाँ बाबा, Rohit.
sir, synchronous what is unit of input power to rotor?
No, Baba, it is not the input power, it is the unit of torque, I told you. So it is not the power, it is the unit of torque, I told you.
It is equal to rotor input.
Yeah, it is not rotor input. So the value of that torque in synchronous watt is the value of the rotor input. Understood? The units are the units for torque and the value will be equal to the rotor input.
Okay, sir.
Understood?
Okay, sir.
Right. Right, Sharath. Cheluri Sharath.
Good evening, sir.
Good evening, ma.
Sir, in high slip operation, you told us, sir, electromagnetic torque is inversely proportional to slip.
Correct.
At that time, the motor draws reactive power.
The active power drawn will be reduced. Why? Because the power factor is reduced. Why? Because when the motor speed is away from synchronous speed, the rotor frequencies will be very high, right?
Yes.
The reactance part will be very high. Then what happened to the resistance part in that case? Starts decreasing.
Yes.
That SX2 naught whole square will be dominating that R2 square. Then what happened to the power factor of the rotor?
Power factor decreases.
Then active power drawn
Decreases.
The torque which depends on that will decrease.
Decrease.
Understood?
Yes, sir. I understood that. But as it draws reactive power, which is used for magnetic flux creation, no, sir.
Yes, that is the only thing. But for torque production, what is required?
For torque,
active power is required.
yes.
Understood?
Okay, sir.
Right.
Yeah. Okay, sir. That's it.
Right. Okay. Right. So no one is raising the hands. I'll stop for today. Right. Thank you.